Hello class. What we're going to talk about today is the shapes of polynomial functions. Right? Now polynomial functions have got all these wiggles and wobbles and stuff like that. And we're going to talk about what those look like and how many shapes they could have, how many turning points and all that. Now the first thing we're going to talk about is the location principle. And what the location principle says that if you have some polynomial function with a and b that are real numbers, such that f of a is less than 0 and f of b is greater than 0, then the function will have at least one 0 between a and b. And what they said is really complicated, the way they said it. What this basically comes out to is this. If y value of x equal a is less than 0, and then if you plug in b and you get y value greater than 0, then somewhere in between there you have to have y equals 0. Right? As somewhere from here to there, you have to get a 0. Might be 2 or 3, but you can have at least 1. Alright, because it could come up and come down and then go up before it gets back to here. That's all it says. So what we can do with this, we want to find all the real zeros of f of x, where f of x is 6 times x cubed plus 5x squared minus 17x minus 6. So let's take a look at this. Step 1, we could use a calculator to come up with a table. And if you look at this table here, we see that at x of 1, y is negative, and at x of 2, y is positive. So we must have an answer somewhere in between 1 and 2. So what we can do is we can use our rational root theorems, p's over q's, right? And remember, p comes from the factors of the p comes factors of the constant, q is factors of the leading coefficient, right, which in this case those are the same numbers. So here's all possible p's, all possible values of q, and so we need some fraction that's going to fit somewhere between 1 and 2. And we see the only combination of that would be 3 halves. Right, that would be 1 1/2. Anything else is going to be less than 1, or it's going to be 2 or greater. Right? So it's got to be 1 1/2. So that's what we have. And we can use synthetic division to confirm that it's that. And we can then go about finding the rest of them. Right? Divide that out, gives us a smaller quotient, and then we can either factor it or do something, or a quadratic formula. In this case, we factor it out. And then we use our factors and we say, okay, the answers must be 3 halves. This would be negative 1/3, and here we have negative 2. Right? And that's what the location property says. It says that you have a negative and a positive. Your 0 has to be somewhere in between. That's it. Not a big deal. Now, the other thing about polynomial functions, what we notice we see all the time, is they wiggle. Right? They go up and down and up and down and up and down. And they have all these turning points. Each time it turns, this is a local maximum or a local minimum. This is a vertex, all right? Also referred to as the extrema. Another word you could use instead of local maximum, they may call it the relative maximum. Relative to the stuff around it, it's higher. Compared to everything in this location, it's the lowest, right? Now, remember you have function increasing. If you go from left to right, your function is going up. Decreasing if your function is going down from left to right. Always move left to right. And so we have all these turning points. Well, some bright guy a long time ago figured out, said, how many turning points will we have? And he came up with this. The graph of every polynomial function with degree of n, whatever n is, has at most n minus 1 turning points. So for example, this could be a third degree function, right? It could be cubic. And so it would have 3 minus 1, so 2 turning points. Here's one turning point. Here's one turning point. It might have less than that. Don't know. But it can't have more than that. So a fourth degree function could have at most 4 minus 1, so 3 turning points. Right? So you go up, turn around and go down, turn around and go up, and then turn around and go back down. All right? Also, if a polynomial function has n distinct real zeros, then its graph will have exactly n minus 1 turning points. So here you see this one has 3 different zeros, and so it has 2 turning points. Okay, so let's take a look at this. We're going to graph this function. We're going to identify the x-intercepts, the points where the local maximums and minimums occur, and then we're going to tell where is the function increasing or decreasing. Now before we do that, we just want to look at this and how many turning points could this function have? It could have 2. Degree is 3, so the turning points it could have 3 minus 1, so 2 turning points. So first thing we're going to do is says to graph it. So there it is, graphed. Alright, and I just did that in my calculator. Now, where are the x-intercepts? Well, we could go about and find it with the zeros and stuff, but we're just going to use the calculator. So I'm going to open up my calculator here. This is 84. If you have an 83 or an 82, it works the same way. If you have one of the more advanced ones like the Inspires or the 95s or something, it's going to look slightly different. But they all have this. So we're going to go and we are going to calculate first the x-intercepts. There's a couple of ways we can do this. One way we can do this is using the zero function, which I don't really like, so I'm going to show you a different way. And that is the intersect function, which works a lot better and a lot faster. Now, in order to intersect, we have to have 2 lines to intersect. And as you see, I've only got one line here, only one equation. So I need to get another. I'm looking for the x-axis, so that would be y equals 0. And it's going to graph that, and you can't see anything because it's a black and white thing. So what I'm going to do now is calculate the intersection. So the second, calc 5. And as you see, now I have 2 lines, 2 curves there. I'm going to arrow over to the one I want, to the intersection, which is right there. If I had more than one intersection, I do this, go to the one I want, then go to another one. And I'm just going to hit enter, 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 and there's my intersection at negative 1.195, blah, blah, blah. So we're going to round that off, and we've got an x-intercept at approximately negative 1.2. Now, we need to find what it asks for, local maximums and local minimums. So see, I have a local maximum here, a local minimum there. We're going to find those. And again, we're going to do this in the calculator. If you want to do this another way, take calculus. But for right now, we're in algebra 2, so we're not going to mess with that. So again, second calc, and we'll find the maximum first because it's just the first one that comes left to right. So the maximum, option 4. You notice it's asking for a left bound. What that means to do is be somewhere on the left of the maximum. And hit enter. Then it asks for the right bound. So we're going to go somewhere to the right of the maximum. So there's my cursor, somewhere to the right of the maximum. Hit enter. And notice I have these 2 little arrows. That's going to tell the calculator to only look for a maximum in between these, because I might have more maximums. And this lets know which one I want. And we hit enter again. And I get this, 1.5219e to the negative 6. That e is the calculator's form of scientific notation. So this is 10 to the times 10 to the negative 6. So that's a decimal, 6 zeros, and then a 1. So this is effectively 0. So 0, 6. There's my maximum. All right, so we have a local maximum at 0, 6. Now I need to find the local minimum. So we're going to go second, calc, come down to minimum, option 3. And I'm going to do the same thing. Left bound, so move my cursor to the left of the minimum, that vertex down there. Hit enter. Do my little arrow right there. Move it to the right of the vertex. Hit enter. Got another little arrow to tell it where to find that minimum. You can move closer if you want, it doesn't really matter. And hit enter one more time. And I get 2.00000.62. So this is effectively rounded to the nearest millionth place, 2. So I've got the minimum at 2, 2. And I'm not entirely sure, oops, wrong button, why the calculator sometimes gives you this or that e to the negative 6. It goes through some little algorithm, and sometimes it doesn't do it far enough. And so it doesn't get quite to the exact thing, but it gets really close. So there's my local maximum, there's my local minimum, And there's my x-intercept. I only have one of each on this one. And so next it wants intervals where the function is increasing or decreasing. So we see the function is increasing in two places. It's increasing right here on the left of this maximum, and it's increasing to the right of the minimum. So that would be to the left of 0, to the right of 2. Remember, these intervals are always looking at x values. So, oops, let's move that over. You can't see it because I'm in the way. Let's move me down. There we go. So the function is increasing on the interval from negative infinity to 0, because it starts way over here and up to where x equals 0, and from 2 to positive infinity. So starting at positive 2 up to positive infinity, it's going to keep going up forever. Alright. And let's move it back up there. Right. The function is decreasing in between these two extrema here, in between these vertices. And so on the interval from 0 to 2, this is not an ordered pair, this is an interval. Another way you can do this, and some professors prefer this better, so if your professor does, here it is. And this is with inequalities. So when x is less than 0, the graph is increasing. When x is greater than 2, the graph is increasing. And when x is between 0 and 2, the graph is decreasing. So that's another way you can do this. So I want you all to do one on your own. This one's going to be a bit more complicated. Real quickly, how many turning points could this function have? 3. Right? 4 minus 1. So it could have 4 turning points, could have 4 zeros. So I'm going to do this all in the graph. So just graph the equation, calculate the x-intercepts, calculate the maximums, calculate the minimums, and then where is the function increasing or decreasing. So pause the video and work this out and then come back. Alright, let's see how you did. First, we need the graph. There's the graph. So we see this does have 1, 2, 3, 4 x-intercepts, 3 turning points. So we have 3 extrema, 2 minimums, 1 maximum. And let's see, here we go. So the x-intercepts, and we just did this all in the calculator, so that's what you should have got for your x-intercepts. Here's the local maximum, that one, not that. Here are the 2 local minimums, and here's the intervals where it's increasing, intervals where it's decreasing, or if you prefer the inequality notation, there it is there. Alright, so hopefully that was useful. Remember, we're just going to do this in the calculator. If you want to do it by hand, take calculus, and you can figure out how to come up with those maximums and minimums. But for right now, for Algebra 2, we're just going to use the calculator to get those. And that's that. I hope that helped.